Imagine looking up at a night sky that still appears calm, ordered, and full of distance, only to realize that the fate of every star, every galaxy, every atom, and every living thing may already have been decided by something we cannot see. Not by fire, not by impact, not even by gravity in the form we first learned to trust. The universe is expanding, and for a long time that much felt manageable. But the deeper we looked, the stranger the picture became, because the expansion was not slowing down, it was speeding up. And once that became clear, the question was no longer simply how the universe began. It became something darker and far more unsettling. What kind of universe accelerates toward its own ending? I'm Christopher Vale, and you're watching Sleepy Explorer. Join me today as we explore the hidden force that may already be writing the last chapter of the cosmos. Together, we're going to follow how one invisible ingredient can turn the future of the universe into a branching map of radically different endings. To understand why this question matters so much, it helps to begin with the most familiar force of all. Gravity is the force that shapes the visible architecture of the universe. It binds planets to stars, stars to galaxies, and galaxies into larger structures. On everyday scales, and even on the scale of solar systems, it behaves exactly the way intuition tells us it should. Matter pulls matter inward. Things that are moving apart should gradually lose speed under that pull, while things already falling together should accelerate toward one another. So when astronomers first thought seriously about the expanding universe, they expected gravity to act as a brake. The universe had been expanding since the beginning, yes, but all the matter within it should have been tugging against that motion. However immense the original expansion may have been, gravity should have been slowly trying to reel it back in. That expectation was so natural that for a while it felt less like a theory and more like common sense written into the cosmos. And yet nature has a habit of making common sense look provincial. By the end of the 20th century, astronomers had begun measuring very distant exploding stars called supernovae with extraordinary care. These explosions can act like cosmic distance markers, allowing us to compare how bright they should be with how bright they appear, and from that infer how far away they are and how space has stretched during their journey. It was painstaking work, but the result was devastatingly clear. The expansion of the universe was not slowing down, it was accelerating. That single reversal changed the emotional tone of cosmology almost overnight. Until then, the universe could still be imagined as a great outward rush, slowly tiring with age. After those measurements, it looked more like a system being driven from within by something new, not merely coasting, not merely surviving its beginning, being pushed. The universe, on the largest scales, was behaving as though empty space itself had acquired a strange and persistent urge to grow. We gave that mystery a name: dark energy. That name can sound more informative than it really is. It does not tell us what dark energy is in the way that the words neutron star or black hole tell us something concrete about the object being described. It is closer to a label placed over ignorance, though not an empty one. It is a name for whatever is causing the expansion of the universe to accelerate. It is a placeholder for an effect that appears real, even though its underlying nature remains uncertain. And that uncertainty is exactly why the end of the universe is still open. If dark energy were just another detail in cosmology, then not knowing its identity would be frustrating but tolerable. The problem is that its identity appears to decide everything. Depending on what dark energy truly is, the expansion of the universe may continue forever in much the same way it does now. Or it may strengthen until it tears all structure apart. Or it may weaken, allowing expansion to stall. Under some possibilities, the cosmos cools into silence. Under others, it collapses, rebounds, or slides into something even harder to imagine. At the top of the puzzle sits one hidden cause. At the bottom waits the fate of everything. That gives the whole subject a peculiar tension. We are not dealing with 4 or 5 unrelated endings competing in a kind of cosmic mythology. We are dealing with one present mystery unfolding into several future possibilities. The branching happens because different theories of dark energy behave differently over time, and each version of that behavior carries a different answer to the same terrible question. How does a universe die? Most of the serious possibilities begin with one of two broad ideas. The first is that dark energy is built into the vacuum itself, meaning empty space is not truly empty, but possesses an intrinsic energy. The second is that dark energy comes from a field, something more dynamic that can evolve, gain or lose strength, and steer the expansion of the universe in changing ways. Those two broad families already tell us something important. The future is not just about how much dark energy exists. It is about whether dark energy is static or alive to time. Let us stay for a moment with the first possibility, because it is also the most deceptively simple. Suppose dark energy is the energy of the vacuum itself. Not a field rolling downhill, not a temporary phase, not an unstable ingredient waiting to transform, just a constant property of space. That would mean the acceleration we observe today is not a passing condition. It would continue for as long as the universe continues. Space would keep stretching. Distances between large cosmic structures would keep increasing. And at first, that might not sound like a dramatic ending at all. After all, there is enough mass concentrated inside galaxies, and especially inside our local gravitational neighbourhood, to resist the feeble influence of dark energy on small scales. The Earth would not be peeled away from the Sun by this effect. The Sun would not be ripped from the Milky Way tomorrow, because space has decided to expand a little faster. Dark energy is cosmological in temperament. It reveals itself across enormous distances, where the pull of matter becomes diffuse, and the expansion of space has room to dominate. This is one reason the problem can feel abstract at first. The universe can be moving toward an extraordinary end, while leaving local reality looking almost untouched for a very long time. A stable vacuum does not announce itself with panic. It begins with separation. Far beyond our galaxy, and beyond the small cluster of galaxies gravitationally tied to us, other galaxies are already being carried away by the expanding fabric of space. As acceleration continues, more and more of them will pass beyond a threshold known as the cosmic event horizon. The comparison to a black hole is useful here, not because the universe is becoming one, but because the logic is similar. Once something crosses that horizon, it is no longer part of a future we can reach, influence, or even communicate with. Its light may continue arriving for a time, growing dimmer and redder as space stretches it, but eventually even that final trace fades. So one by one, the wider universe would disappear. Not physically vanish, at least not in the ordinary sense. It would still exist, but it would become observationally inaccessible. A future civilization living trillions of years from now could look outward and see only its own surviving island of structure, with no evidence that the cosmos was ever populated by countless galaxies scattered across unimaginable distance. The universe would not simply become emptier, it would become smaller from the point of view of knowledge. Whole chapters of cosmic history would slide beyond the boundary of proof. That alone is eerie enough. But it is only the beginning of what a stable vacuum implies. Because even if local gravity protects structures like galaxies from being torn apart by cosmic acceleration, it does not protect them from time. Stars burn through their fuel, planets cool, temperature differences flatten. Processes that seem lively from our current vantage are all temporary ways of spending free energy. Every star that shines is participating in a one-way conversion. Every weather system, every orbiting world, every chemical metabolism, every living organism is living off gradients that do not last forever. This is where the second law of thermodynamics enters the story like a quiet verdict. Left to itself, a system tends toward higher entropy, toward more dispersed energy and fewer useful differences. That does not mean the universe is rushing chaotically toward disorder in a dramatic sense. It means that the ability to do anything interesting slowly drains away. Stars stop forming. Existing stars die. The leftovers collapse into dense remnants. Even black holes, given incomprehensibly long timescales, can evaporate through quantum effects, bleeding away what once seemed eternal. The destination of that process is often called heat death, though the name is misleading if taken literally. It does not mean the universe ends in flame. It means the universe ends with no meaningful flow of heat at all. No usable gradients, no engines, no chemistry of consequence, no dawn because there is nothing left to illuminate, and no difference left to exploit. It is an ending defined less by destruction than by exhaustion. And perhaps that is why it feels so unnerving. A big collision has drama. A final implosion has violence. But a universe entering thermal equilibrium dies by becoming unable to surprise itself. There is, at the far edge of this idea, one strange and almost philosophical twist. Roger Penrose proposed that an unimaginably old, radiation-dominated future might under certain conditions become indistinguishable from a beginning, allowing one cosmic era to feed into another in a conformal cyclic sequence. It is a beautiful thought, and a provocative one, though the evidence for it remains thin. Still, it introduces a note that matters for the tone of this whole investigation. Even at the end of a story this large, physics sometimes leaves a crack open where intuition would have expected a wall. But before we drift too far into that possibility, a more urgent complication intrudes. The quietest future only follows if the vacuum is not merely real, but stable. And some of the physics we know best has given us reason to wonder whether empty space is really as secure as it looks, or whether the calm surface of the universe may be hiding a deeper drop beneath it. If that calm surface is truly solid, then the future becomes brutally simple. In the most conservative picture, dark energy is nothing more exotic than a constant property of empty space. It does not strengthen, it does not weaken, it does not tunnel into a new state. It simply remains what it is now, forever. In modern cosmology, this idea is often tied to the cosmological constant, the old term Einstein once introduced for a different purpose and that later returned wearing a far stranger meaning. There is something almost elegant about that possibility. It asks us to believe that the universe is not racing towards some hidden transition, but steadily obeying a rule that has already revealed itself. Space expands. Empty space carries a tiny but persistent energy, and because more space means more vacuum, and more vacuum means more of this same outward effect, the acceleration continues without needing to become dramatic in any sudden way. That last point matters, because the big freeze is often imagined incorrectly. It does not mean that one day the universe flips into a visibly different mode and everything begins rushing apart before our eyes. For any civilization living inside a gravitationally bound system, the change would be slow almost to the point of invisibility. The stars would still rise, galaxies would still glow, local gravity would still hold matter together where matter is dense enough to resist the gentle repulsive influence of dark energy. This is why our own cosmic neighbourhood is so important. The Milky Way is not alone, but neither is it adrift as a single isolated island. It belongs to a small gravitationally bound collection of galaxies, often called the local group. That group includes Andromeda, the Triangulum galaxy, and a crowd of smaller satellite galaxies, all close enough that their mutual gravity can still overcome the expansion of the wider universe. So in a stable vacuum future, these nearby systems do not simply disappear from one another, as though everything were being pulled apart indiscriminately. In fact, the opposite happens on those local scales. The Milky Way and Andromeda are expected to merge far in the future, long before the deeper freeze of the cosmos becomes dominant. Stars will mostly pass by one another unharmed, because the space between them is so vast, but their galaxies will distort, intermingle, and eventually settle into a new, larger structure. So even inside a universe condemned to growing emptier, local history still continues for a while. There are collisions, mergers, remnant stars, and long afterlives of structure. But outside that shrinking island of intimacy, the story is merciless. As cosmic expansion accelerates, more distant galaxies cross the cosmic event horizon. That phrase can sound abstract, but its meaning is concrete enough to be haunting. Light from those galaxies may still reach us for some time, stretched by the expanding universe until it becomes dimmer, redder, and harder to detect. Yet there comes a point beyond which no new signal they emit can ever arrive. The future stops carrying them toward us. They are still out there, but no longer in causal contact with our part of the universe. You can think of it as a kind of soft erasure. There is no explosion, no grand farewell. One by one, the rest of the cosmos recedes beyond the boundary of interaction, then beyond the boundary of observation, and finally, beyond the boundary of practical belief. A civilization born sufficiently late in this future might look into space and conclude, quite reasonably from the evidence available to it, that the universe contains only one galaxy-like structure suspended in darkness. And that would not be a failure of intelligence. It would be a consequence of cosmology. There is something deeply unsettling about this, because it turns scientific knowledge into a temporary privilege. We often imagine progress as a one-way road, as though future minds must know more than present ones simply because they come later. But in a universe dominated forever by stable vacuum energy, some of our most profound discoveries may belong only to a relatively early era. We live at a time when the sky still carries the memory of a larger universe. That will not always be true. The loss does not stop at galaxies, it moves inward, from the scale of cosmic structure to the scale of process itself. Everything we call activity depends on gradients. A star shines because conditions in its core differ from conditions at its surface. A planet has weather because energy arrives unevenly, moves and dissipates. Life survives by exploiting chemical imbalances. Thought itself is powered by ordered flows inside highly organized matter. None of that is permanent. Every process feeds on a difference and leaves behind a little less difference than before. This is why the second law of thermodynamics is not just another law of physics, but one of the great narrators of time. It tells us that while local pockets of order can certainly emerge, especially in a young and energetic universe, the overall tendency is toward equilibrium. Not the kind of equilibrium that looks balanced and serene in a human sense, but the kind that leaves nothing left to happen. A universe can remain full of particles and still become existentially empty if those particles no longer participate in any meaningful transformation. Stars are the first great casualty of that long drift. The ones alive now are already living on borrowed fuel, converting hydrogen into heavier elements and radiating the energy difference into space. Some will die quietly, swelling into red giants and shedding outer layers before leaving behind white dwarfs. More massive stars will end more violently, collapsing into neutron stars or black holes. New stars will continue to form for a long time from the gas still available in galaxies, but not forever. The supply thins, structure ages, the star-making epoch ends. After that, the universe enters a far stranger era, one in which the dominant inhabitants are stellar remnants. White dwarfs cool, neutron stars fade, brown dwarfs linger as dark, failed embers. Planets roam or freeze. The galaxy, if we still call it that, becomes less a luminous city and more an enormous graveyard of compact leftovers orbiting through deepening dark. On these timescales, familiar astronomy begins to look like archaeology performed after the builders are gone. Given long enough, even that remnant era does not last. Orbits can destabilize through countless weak interactions. Some objects are flung away into intergalactic darkness, others spiral inward. Encounters, though rare, reshape the population over almost absurd spans of time. Matter that is not ejected often ends up consumed by black holes, either directly or through chains of mergers and slow gravitational capture. What once seemed like a galaxy full of variety gradually simplifies into a smaller set of dominant survivors. And then the black holes inherit the future. This too can be hard to accept, because black holes feel like endpoints already. They swallow matter, trap light, and appear to stand outside ordinary decay. But even they are not immune to time. Through a quantum process now known as Hawking radiation, black holes are expected to lose mass with extraordinary slowness. A black hole is not a perfectly sealed vault. It leaks. Not quickly enough to matter on any human scale, or even on the scale of stars and galaxies as we usually imagine them, but inevitably all the same. So the final custodians of structure are themselves temporary. When the black holes evaporate, what remains is a thin bath of low-energy radiation, and whatever elementary particles have survived the eons without further transformation. By then, the notion of a galaxy has lost almost all practical meaning. There may still be matter, there may still be relics, but there is no engine left, no strong temperature contrast, no accessible reservoir of free energy from which complexity can rise again. The universe has not been destroyed. It has been drained of drama. That is the true meaning of heat death. The name often misleads people into picturing a universe burned out from excess heat, but the phrase points instead to the end of heat flow. A warm object beside a cold one can do something. Energy can move. Work can be extracted. History can happen. Once everything is leveled out, or nearly so, the possibility of meaningful change collapses. The universe becomes cold not merely in temperature, but in narrative. It is no longer headed anywhere, because it no longer contains the asymmetries that make events possible. If you try to imagine how far away such a future lies, language starts to fail. The current universe is nearly 14 billion years old, and yet the timescale on which full heat death emerges is so much larger that ordinary comparisons break down. We are not speaking of twice the present age, or 10 times, or 1,000,000 times. We are speaking of lengths of time that make the entire history of stars look like a brief opening act. The final stillness arrives so far ahead that human intuition cannot hold it comfortably. And yet the emotional force of the idea does not come from soonness, it comes from inevitability. A stable vacuum gives us a universe that does not fail through accident, miscalculation, or cosmic violence. It fails because the rules themselves point toward thinning, cooling, flattening, and silence. There is no villain, no hidden sabotage, no great impactor from beyond. There is only a universe with enough initial structure to become interesting, and enough time to become exhausted. This is the point where some thinkers have tried to rescue meaning from what looks like absolute finality. Roger Penrose, among the most imaginative physicists of the modern era, proposed that the extremely distant future of such a universe might not be as terminal as it appears. In his conformal cyclic cosmology, a universe emptied of massive structure and reduced to radiation may, in a certain geometric sense, become equivalent to a new beginning. One cosmic age could flow into another, not through a conventional rebound, but through a profound redescription of what counts as size, scale, and time in an almost structureless cosmos. It is a beautiful idea, perhaps too beautiful. Evidence for it remains contested and thin, and it certainly does not rescue individual stars, planets, or civilizations from the fate described here. Even if Penrose were right, the universe we know would still dissolve beyond recognition long before any such rebirth became relevant. But the proposal matters because it reveals something subtle about cosmology at its edge. Even the bleakest future can open, under enough pressure, into another question. Still, if we are trying to understand the most likely end of the universe, rather than the most poetic reinterpretation of it, then the Big Freeze remains the cleanest consequence of stable vacuum energy. It is simple, it is mathematically natural. It does not require dark energy to become stronger, weaker, or more capricious than it appears, and for precisely that reason, many cosmologists have treated it as the default destination of an accelerating universe. But simplicity is not the same thing as security. Because the more carefully physicists have looked at the vacuum, the less obvious its permanence has seemed. The field that gives elementary particles their masses may not sit in the deepest possible state. Theoretical landscapes inspired by string theory hint that apparently stable positive vacua might be difficult to sustain. And if the vacuum we inhabit is not the true ground floor of reality, then the quiet freeze we have just followed across unimaginable ages may never get the chance to arrive at all. The universe may not be gliding toward a final stillness. It may be waiting above a trapdoor. A trapdoor hidden not in space but in the laws of physics themselves. The unsettling possibility is that what we call empty space may not be truly stable. It may only be locally stable. Stable in the way a stone can rest for a very long time in a shallow hollow on a hillside, while a deeper valley waits farther down. From where the stone sits, nothing seems wrong. It can remain there through wind, rain, and ages of quiet. But it is not in the lowest possible state. It is only in a state that looks final until some deeper transition becomes possible. That is the idea behind a metastable vacuum. To see why this matters, we need to be careful about what the vacuum means in modern physics. It is easy to hear the word vacuum and picture literal emptiness, a perfect void containing nothing at all. But in quantum field theory, the vacuum is not nothingness in that simple sense. It is the lowest energy configuration of the fields that fill the universe. Even when there are no particles present in a region, the fields themselves remain. And those fields can, in principle, sit in different energy states. That sounds abstract, but one of the most important fields in all of physics already gives us a reason to take the possibility seriously. The Higgs field is woven throughout the universe, and its interaction with other particles helps determine their masses. Without it, the structure of familiar matter would be radically different. The electron would not behave the way it does. Quarks would not combine into the same kind of stable particles. The chemistry from which stars, planets, and life emerge would collapse before it began. So if the Higgs field were sitting not in its deepest possible vacuum state, but in a merely temporary one, the implications would be almost impossible to overstate. Current measurements suggest that the Higgs field may lie in a delicate position, perhaps not fully secure, perhaps balanced in a state that is stable enough to survive for absurdly long times, but not necessarily forever. This does not mean disaster is expected tomorrow, or next year, or even in any period that would feel meaningful to human history. Most estimates place any such decay, if it is possible at all, on timescales so vast that they make even the big freeze look patient. But the emotional impact of the idea does not come from urgency. It comes from what kind of ending it would represent. Because a metastable vacuum does not end the universe by letting it wind down, it ends the universe by changing the rules. The mechanism most often discussed here is quantum tunneling. In everyday life, if a ball sits in a valley separated from a deeper valley by a hill, it cannot get to the lower one unless it is pushed up and over the barrier. Classically, that is the whole story. But quantum mechanics allows for stranger behaviour. A system can, under the right conditions, transition through a barrier without climbing over it in the ordinary way. It is not magic. It is not particles cheating the rules. It is the rules. And when applied to fields rather than to small objects in a laboratory, the consequences become cosmic. A better image than a ball may be a landscape of energy spread beneath all reality. The vacuum we inhabit might be one basin in that landscape, not the lowest basin, just one that has lasted. If a deeper basin exists, then the vacuum could, in principle, tunnel into it, and once that happened, a new state of space would begin to form and expand. This is where the whole idea becomes difficult to narrate without sounding fictional, because the event would not resemble any ordinary catastrophe. There would be no warning siren, no growing instability visible in the sky, no slow conversion allowing anyone to measure the danger and react. A bubble of lower energy vacuum would appear somewhere, then expand outward at a speed approaching that of light. Inside that bubble, the universe would obey a different set of physical conditions. And that phrase, different physical conditions, is doing enormous work. The masses of particles depend on the state of underlying fields. If the Higgs field dropped into a new vacuum, particles like electrons and quarks could acquire different masses than the ones they have now. That alone would be enough to rewrite the structure of matter. Atoms depend on exquisitely specific balances. The sizes of electron orbitals, the stability of nuclei, the strength of chemical bonds, all of it rests on the numerical relationships physics currently permits. Change those relationships enough, and atoms as we know them no longer exist. Molecules no longer exist. Biology no longer exists. The materials of planets and stars no longer organize themselves in the same way. Even the word destruction is too ordinary for this. Destruction usually means taking something stable and breaking it apart. Vacuum decay would be more like replacing the template from which stability itself is built. There is another reason physicists take such scenarios seriously. and it comes from an entirely different line of thought. String theory, whatever its ultimate fate as a description of nature, has suggested that the landscape of possible vacuum states may be vast. Instead of one unique ground state for the universe, there could be many metastable configurations with different properties. Some could support positive vacuum energy, others could support negative energy. Some might be comparatively long-lived, others might be easier to tunnel into. The theory has not delivered a decisive prediction here, but it has pushed the imagination of cosmology toward a far more crowded and less reassuring picture of the vacuum than classical intuition would ever have permitted. In that picture, our universe may not be resting on bedrock. It may be perched. There is something especially cruel about the contrast between this scenario and the Big Freeze. The Big Freeze, for all its bleakness, at least allows complexity to age. Stars live their lives, galaxies evolve, black holes linger. Time gets its fast and solemn say. Vacuum decay does not care about any of that. It does not negotiate with civilizations, or wait for stars to die naturally, or preserve the continuity of cosmic history. It inserts a discontinuity into the middle of everything. One set of physical laws ends. Another begins. From the point of view of anything made under the old laws, the change is unsurvivable. And unlike most endings we imagine, this one is not localized in any intuitive way. If a star explodes, you can at least point to the star. If a galaxy collides, you can point to the galaxies. But vacuum decay, if it happens, is not the destruction of an object within the universe. It is a change in the state of the universe itself, propagating through space and redefining what that space allows. Could we ever see it coming? Almost certainly not. That is one of the reasons the idea has such eerie force. If the bubble expands at nearly the speed of light, then by the time information about it reaches any observer, the bubble itself arrives with that information. There is no gap between diagnosis and impact, no heroic evacuation, no final message sent ahead. A lower vacuum state would not be an approaching stormfront. It would be the cancellation of approach as a meaningful category. Of course, honesty matters here. None of this means that vacuum decay is established fact. It is a possibility implied by the structure of some of our best theories, not a scheduled event on a cosmic calendar. The uncertainties are enormous. They include the precise values of particle masses, the behavior of fields at energies far beyond our current experiments, and whether our theoretical frameworks remain trustworthy all the way up those scales. In other words, this is not a reason to panic. It is a reason to respect how thin the line can be between apparently serene physics and astonishing consequences. And there is an even deeper uncertainty still. Suppose such a transition occurred. What would the new vacuum actually be like? That depends entirely on where the universe lands. If the new state simply altered particle masses, then the result would already be fatal to familiar structure. But in more elaborate scenarios, especially those inspired by richer field landscapes, the new vacuum could also bring entirely new particles into play, remove old symmetries, change the strength of interactions, or perhaps steer cosmic expansion onto a completely different path. In principle, the new universe inside the bubble might keep expanding, stop expanding, collapse, or do something more exotic still. We cannot say with confidence because we do not know what the destination vacuum would be. So unlike the Big Freeze, vacuum decay does not give us a crisp picture of the very end. It gives us a sudden break in the middle of the story, after which the rest becomes unreadable. This is where a subtle distinction becomes important. In the stable vacuum picture, dark energy is still mysterious, but its behavior is simple enough that we can project the future cleanly. In the metastable vacuum picture, dark energy may again belong to the vacuum, but that same vacuum has a hidden instability that makes long-term projection fragile. The universe may seem committed to eternal acceleration, yet underneath that apparent commitment lies the possibility of a transition that interrupts everything before the freeze is complete. So on one side we have a cosmos that dies by exhaustion, on the other one that may die by replacement. Neither option is comforting, but both still share the same basic assumption, that dark energy is vacuum energy. and that assumption may itself be wrong. Because there is another broad way to think about dark energy, one that changes the story from a fixed background property into something more like a moving actor. Instead of belonging to empty space in a perfectly constant way, dark energy might come from a field whose energy changes over time. And once that door opens, the future stops being a choice between stable vacuum and unstable vacuum. It becomes a much wider landscape in which dark energy can weaken, strengthen, reverse the expansion, tear structure apart, or even drive the universe through cycles of collapse and renewal. A constant vacuum gives us one clean tragedy and one hidden trapdoor. A dynamical field gives us an entire map of possible endings, and some of them are stranger still. And some of them are stranger still, because once dark energy becomes a field rather than a fixed property of the vacuum, the future of the universe stops depending on a single yes or no question about stability. It starts depending on how that field moves. Does it lose energy as time passes, like something rolling downhill through a rough landscape? Does it remain almost unchanged for so long that it merely imitates a cosmological constant? Or does it do the most disturbing thing of all and grow stronger with time, turning a gentle acceleration into a catastrophic one? This is the essential difference between vacuum energy and a dynamical field. A perfect vacuum state can sit there, unchanged for an eternity, unless some tunneling event interrupts it. A field, by contrast, can evolve continuously. It has a history. It can respond to the expansion of the universe, to its own internal potential, and to the changing geometry of space-time around it. That makes it harder to predict, but it also makes it richer as a source of possible endings. One of the most intuitive ways to picture such a field is as a ball moving across a landscape. The shape of the landscape determines where the field wants to go, and the expansion of the universe acts a little like friction, resisting rapid motion. In the simplest versions, that friction drains the field's energy over time, so the field gradually settles down. If dark energy works like that, then its future influence may slowly fade, or it may decline so gradually that for all practical purposes, it behaves almost like a constant. That gives us our first branch. Suppose the field always remains positive and changes only very slowly. In that case, the future can look remarkably similar to the stable vacuum picture we have already followed. The expansion continues to accelerate, the event horizon keeps pushing the wider universe beyond reach, and the long thermodynamic fade still leads toward heat death. The difference is not so much in what happens as in why it happens. Instead of a fixed vacuum energy, the acceleration is maintained by a field that is changing so lazily that the cosmos cannot tell the difference. That is an important reminder. Different physics can lead to very similar skies. Two universes may age in almost the same visible way, while resting on very different underlying causes. Cosmology is full of such ambiguities, where what we observe is a shadow cast by multiple possible realities. But a field also allows a gentler possibility that the vacuum picture does not. It can weaken fast enough for the acceleration to end. If that happens, the future changes subtly but significantly. The universe does not suddenly reverse or collapse the moment dark energy fades. It simply loses the driver that was making the expansion speed up. After that, the long-term story depends more heavily on the geometry of the universe itself, on whether space is flat, open or closed in the large-scale sense. In a flat or open universe, expansion can continue without acceleration, and the cosmos may still drift toward a form of heat death, but it would do so without the same isolating event horizon that defines the Big Freeze. That detail matters more than it may first seem. In an eternally accelerating universe, more and more of the cosmos is carried permanently out of contact. In a universe where acceleration stops, distant galaxies can remain in principle observable for much longer, even as stars age and entropy continues its slow work. The ending is still cold, still sparse, still thermodynamically bleak, but less severed. It is, in a certain sense, a quieter tragedy. Not a locked room shrinking around us, but an ever-thinning universe that remains at least partially connected to itself. There is something almost merciful about that version of the future. It is still finite in opportunity, still headed toward exhaustion, but without the same ruthless erasure of the wider cosmos. If one were forced to choose among bad endings, this might be among the least violent. Yet the same weakening field can also produce the opposite outcome if the universe is closed strongly enough to overcome the remaining outward motion. In that case, expansion does not merely coast onward, it slows, halts, and reverses. Distances that had been growing for billions of years begin to shrink. The universe turns around and starts to fall back in on itself. This is the classical Big Crunch. The phrase has an almost mythic quality because it mirrors the Big Bang so neatly, one beginning in fire and density, one ending in fire and density. But the symmetry should not be overstated. A crunch is not simply a bang in reverse. It is a collapsing universe shaped by whatever structure, radiation, and field content happen to exist at the end of its expansion. Galaxies would not politely retrace their past trajectories. Instead, gravity would begin drawing matter into ever tighter encounters, heating the cosmos, intensifying radiation, and raising the stakes of every remaining structure. If the story ended there, it would already be dramatic enough. But fields introduce another complication during contraction. The same cosmic expansion that acts like friction while the universe grows can flip its role once the universe starts collapsing. What once damped the field's motion can become a kind of cosmic anti-friction, feeding energy back into it rather than draining it away. The field can begin to race. This is where the geometry of the future starts to feel less like a clean script and more like a machine with feedback loops built into its bones. A universe that contracts can make the field evolve faster. A faster field can then alter the collapse itself. Depending on how quickly its energy rises, the ending can take on very different forms. If the field gains energy gradually during the collapse, there may be plenty of time for the universe to complete something recognizably like a big crunch. Structure contracts, temperatures rise, densities increase. The cosmos heads toward a final state of overwhelming compression. That alone is enough to sound terminal. But some models take the idea one step further and suggest that such a collapse might not be the final word. Under the right conditions, an extremely hot and dense contracting universe could transition into a new phase of expansion. This is the Big Bounce. The bounce is one of the most seductive ideas in cosmology because it seems to offer a way around absolute beginnings and endings alike. Instead of one unique origin and one final death, the universe could cycle through eras of expansion, cooling, contraction, and reheating. Our own Big Bang would then not be the first page of existence, but the start of the current cycle. Something came before it, not necessarily stars and galaxies like ours, but a previous cosmic phase whose collapse helped trigger our expansion. That kind of cyclic picture is distinct from Penrose's conformal cycles. Penrose imagines the infinite future of one eon blending into the beginning of another through geometry. A bounce scenario is more directly dynamical. Space contracts, conditions intensify, and some mechanism prevents the final singular collapse, redirecting the universe outward once again. It is a very different style of rebirth, and one that remains highly speculative, though not without serious theoretical interest. There is also a harsher version of this field-driven future. A field may not merely weaken or become negative and help trigger collapse. It may instead grow stronger and stronger while the universe is still expanding. This is the possibility known as phantom dark energy, and it is one of the most extreme endings cosmologists have entertained. In ordinary versions of dark energy, the repulsive effect is powerful only on the largest scales, where matter is diffuse enough for the accelerated expansion to dominate. But if the field's energy density rises over time, that repulsion becomes increasingly important everywhere, not just between galaxy clusters, but eventually within galaxies, within solar systems, and below. The result is the Big Rip. At first, the change would express itself the way dark energy usually does, by accelerating the expansion of the cosmos. But unlike the stable vacuum picture, this acceleration does not remain calm and nearly constant in character. It strengthens. The event horizon does not merely push distant galaxies away, it shrinks inward. Regions that could once communicate become causally isolated on smaller and smaller scales. First, galaxies lose contact with one another, then stars within galaxies, then planets with their stars, and eventually matter itself is no longer safe from the outward surge. That is the true horror of the Big Rip. It is not only a cosmic scale event, it is a scale-by-scale unbuilding of structure. Gravity loses its grip, then electromagnetism loses its hold over atoms and molecules. In the most violent versions, even atomic nuclei are no longer spared. The hierarchy of binding forces that made complexity possible is peeled away layer by layer as the repulsive influence of dark energy becomes overwhelming. Unlike the Big Freeze, which leaves structures intact for ages before entropy quietly empties them, the Big Rip actively dismantles the architecture of reality. And unlike vacuum decay, which changes the rules in a sudden advancing front, the Rip keeps the same general rules while pushing one term inside them to absurd dominance. The universe does not switch to a different operating system. It tears its own current one apart. Some versions of this scenario place the singular finale only a few billion years in the future. That is still unimaginably remote compared with human lifetimes, but cosmologically, it is not so far away. It would mean that the age of stars, galaxies and life occupies not the opening sliver of an almost endless expansion, but a more substantial fraction of the whole story. Fortunately, phantom dark energy remains hypothetical. It is a theorist's warning more than an observational verdict, but it serves an important role in this map of endings. It shows how sensitive the future can be to the equation of state of dark energy, to the relationship between its energy density and pressure. And that is perhaps the deepest lesson of the whole field-based picture. The end of the universe is not controlled only by whether expansion continues. It is controlled by how the stuff driving that expansion behaves under time, geometry, and feedback. A slight difference in how the field rolls can mean the difference between a gentle fade, a collapse, a rebound, or a total shredding of structure. So where does that leave us? It leaves us with a branching tree that is intellectually exhilarating and emotionally destabilizing in equal measure. If dark energy is a field, then the universe may freeze in a way that resembles the vacuum picture. It may drift into a softer heat death once acceleration ends. It may collapse into a crunch. It may rebound into a new cycle. Or it may rip itself to pieces in finite time. The future is no longer one clean line. It is a family of fates emerging from the hidden behaviour of something we still cannot identify with confidence. And that brings us to an uncomfortable point in the investigation. We have now mapped several endings in broad outline, but we have not yet earned the right to favour one over another. We have been following consequences outward from theories, not rebuilding the case from observation inward. Before we can judge which of these futures deserves the most weight, we need to step back from the endings themselves and ask a more basic question. What did we actually see that convinced us the universe was acting strangely in the first place? And what, exactly, do we mean when we say dark energy is there at all? To answer that, we need to strip the mystery back to its observational bones and return to a time when the universe looked far smaller, simpler, and more manageable than it does now. A little more than a century ago, many astronomers still assumed that the Milky Way was effectively the universe. There were stars, nebulae, clusters, and curious fuzzy patches in the sky. But whether those patches were small structures inside our own galaxy or vast star systems in their own right remained unsettled. The cosmos, as far as human confidence was concerned, had not yet become truly enormous. That began to change when astronomers learned how to measure distance beyond the local neighbourhood of stars. One of the most important tools in that effort came from a special kind of star known as a Cepheid variable. These stars brighten and dim in a regular rhythm, and crucially, that rhythm is linked to their true luminosity. Once you know how quickly one of these stars pulses, you can estimate how bright it really is. And once you know how bright it really is, you can compare that intrinsic brightness with how faint it appears from Earth and infer its distance. It was a cosmic ruler, delicate but revolutionary. When Edwin Hubble used Cepheid variables to study what we now call the Andromeda Galaxy, the result pushed Andromeda far beyond the bounds of the Milky Way. That one measurement did more than revise a distance chart, It shattered a worldview. The universe was not a single galaxy after all. It was populated by many galaxies, each containing immense numbers of stars, each separated by gulfs so large that older cosmologies had not seriously prepared us for them. And once the universe became larger, a second revelation followed close behind. Those galaxies were not standing still. Light carries motion inside it. When a source moves away, its light is stretched to longer wavelengths. When it moves closer, the light is compressed. This is the same underlying logic that changes the pitch of a siren as an ambulance passes by, only written into light instead of sound. When astronomers began comparing the known patterns of atomic light with the patterns arriving from distant galaxies, they found something remarkable. Most galaxies were shifted toward the red. They were moving away from us. More than that, the farther away a galaxy was, the faster it appeared to be receding. This did not mean that Earth sits at the centre of everything and watches the cosmos flee from it. A better image is a loaf of rising bread dotted with raisins. As the dough expands, each raisin sees every other raisin moving away, and the more distant ones appear to separate faster because more expanding dough lies between them. In cosmology, the dough is space itself. Galaxies are not simply flying through a pre-existing void. The fabric between them is stretching. This was the birth of the expanding universe in scientific thought, and once that expansion was accepted, the logic of a denser, hotter past became difficult to avoid. If galaxies are farther apart now, they must once have been closer together. Follow that reasoning back far enough, and you arrive at a universe that was once compressed into an extraordinarily hot and dense state. What we call the Big Bang is not an explosion into empty space in the ordinary sense. It is the rapid early expansion of space itself from conditions unimaginably more compact than those of today. At this stage, the story still retained a certain intuitive neatness. The universe expands because it began in an extreme state. Gravity, acting through all the matter in the cosmos, should gradually resist that expansion. The rate may differ depending on how much matter exists and how space is shaped, but the general expectation remained the same. Expansion ought to slow. Even Einstein, whose general theory of relativity had supplied the deeper mathematical framework for modern cosmology, initially resisted the idea of a dynamic universe. His equations naturally allowed for expansion or contraction, yet he preferred a static cosmos, one neither swelling nor collapsing. To force the mathematics into that shape, he introduced an additional term, now famous as the cosmological constant. It was, in effect, a balancing term, something that could counter gravity on the largest scales and keep the universe still. Then the evidence for cosmic expansion grew stronger, and the static universe lost its footing. The cosmological constant seemed unnecessary, even awkward, a mathematical prop from an abandoned stage set. But reality was not finished with it. Because the next great turn in this story came from a different generation of observations altogether. By the late 20th century, astronomers were using distant Type 1a supernovae as standardizable candles, extraordinarily useful explosions whose brightness can be calibrated well enough to probe the expansion history of the universe. These stellar deaths allowed scientists not only to see that the universe expands, but to ask how that expansion has changed over time. And the answer overturned the old expectation. The expansion was not merely continuing, it was accelerating. That was the moment dark energy truly entered the scientific imagination, not as a metaphysical flourish, but as a response to a measurement. Something in the cosmos was acting against the tendency of matter to slow expansion. Something was making the large-scale stretching of space speed up instead of ease down. Whatever its deeper identity, that effect had to be included in our account of the universe. To see why, we need to move from the observational surface of the problem into the language of general relativity. In Newton's picture, gravity is a force between masses. In Einstein's picture, the deeper truth is geometric. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. A planet orbiting a star is not being yanked along a mysterious invisible rope. It is following the straightest path it can through a geometry warped by mass and energy. Once you think in those terms, the expansion of the universe itself becomes part of the geometry. Space is not a rigid stage with galaxies sliding across it. It is dynamic, it can stretch, it can evolve. And the contents of the universe do not just move inside that evolving space. They help determine how it evolves. This is where pressure enters the picture in a way that often surprises people. In general relativity, not only mass but energy density and pressure contribute to the dynamics of space-time. Ordinary matter has positive energy density and effectively negligible pressure on cosmic scales. Radiation has positive energy density as well, and because of the way it moves, it contributes pressure too. In both cases, the combined effect tends to decelerate expansion. They help gravity do what we expect gravity to do. But a component with strongly negative pressure behaves differently. That phrase can sound slippery at first. Negative pressure is not less than no atoms, or some childish subtraction of substance from space. A better way to think of it is in terms of tension. Pull on both ends of a stretched material, and the material is under tension rather than compression. In the cosmological equations, something like that kind of tension in the fabric of space-time can drive accelerated expansion. It acts not by flinging galaxies outward through space like debris from an explosion, but by making the space between large structures stretch faster over time. That is the key conceptual shift. Dark energy is not best pictured as a wind blowing galaxies apart. It is better understood as a property of the universe that alters how space itself evolves. Once that framework was in place, cosmologists began fitting observations from many directions into a common model. The cosmic microwave background, the large-scale distribution of galaxies, the clustering effects associated with dark matter, supernova measurements, and other lines of evidence all pointed toward a startling inventory. Ordinary matter, the atoms that make stars, planets, gas, dust, and us, contributes only a small fraction of the total cosmic energy budget. A larger share belongs to dark matter, the invisible gravitating component inferred from its effects on galaxies and larger structures. And larger still is the component driving cosmic acceleration. Dark energy dominates the present universe. That can be hard to absorb, because it means the material world of direct experience is not the main actor in the cosmos. The things we can touch, see, or build with belong to a minority component. The universe, in the broadest accounting, is ruled by something we do not yet understand, and something else we cannot directly see. At that point, the question became unavoidable. What is dark energy actually supposed to be? Three major lines of thought emerged. The first returned, with a kind of historical irony, to Einstein's cosmological constant. Perhaps empty space itself possesses an intrinsic energy density, constant in time and uniform throughout the cosmos. In that case, the acceleration is not evidence of some new dynamical field at all, but the natural consequence of vacuum energy. The second line of thought tried to connect that vacuum energy to quantum physics. Even what we casually call empty space is not truly featureless in quantum theory. Fields fluctuate. Virtual processes shimmer in and out of possibility. Perhaps the energy of the vacuum comes from those quantum fluctuations. This had a certain elegance, because it linked cosmic acceleration to the restless structure of quantum reality. There was only one problem. When physicists tried to estimate the vacuum energy this way, the answer came out catastrophically wrong. We will come back to that, because it becomes one of the deepest problems in all of theoretical physics. The third major possibility was that dark energy is not truly constant at all, but instead the effect of a field that changes over time, something akin to a cosmological fluid with evolving properties. Quintessence became a common label for this family of ideas. In such models, dark energy is real but not fixed. It can strengthen, weaken, or drift, opening the door to the branching futures we have already explored. And there was one more possibility lurking behind all of these. Perhaps the problem is not a new substance, but an incomplete theory of gravity. Perhaps general relativity, magnificent as it is, changes subtly on the very largest scales, and what we interpret as dark energy is actually a clue that our theory of space-time itself needs revision. That possibility remains alive, though it has proven difficult to turn into a model that fits the data as cleanly as the standard picture. So by this point in the story, we have not solved dark energy. We have only narrowed the style of explanation it seems to demand. Either empty space carries a tiny but persistent energy, or some field evolves across the cosmos, or gravity itself behaves differently on the grandest scales. Each of those possibilities can account for acceleration in principle. Each carries very different philosophical and physical consequences, and each leaves us standing before the same unnerving fact. The universe is accelerating, and whatever is causing that acceleration now dominates the cosmic future. If that were the whole problem, it would already be among the most profound questions in cosmology. But there is another layer beneath it, one that turns dark energy from a mystery about the future into a crisis about the past, and even about our existence. Because once physicists tried not merely to name dark energy, but to calculate how much of it there ought to be, they did not get a small mismatch. They got a number so wildly wrong that, if it were correct, stars, galaxies, planets, and life would never have had the chance to form at all. In other words, the universe should have missed its own chance to become interesting. That is what makes the cosmological constant problem so much more than a technical annoyance buried inside theoretical physics. It is not merely that one calculation comes out wrong. It is that the wrong answer is wrong in exactly the direction that would have erased everything we are trying to explain. The stars should not have formed. Galaxies should not have assembled. Chemistry should not have matured. Planets should not have cooled into stable homes for complex matter. And yet, here we are, on a small rocky world, able to notice the discrepancy at all. To feel the force of the problem, it helps to retrace the history of the universe in very broad strokes. In the earliest moments after the Big Bang, the cosmos was too hot and dense for atoms to exist. Then it expanded and cooled. Protons and neutrons combined into the first light nuclei. Later still, electrons settled into orbits around those nuclei, giving the universe its first atoms, mostly hydrogen and helium. Gravity then began its long, patient work, pulling matter into denser regions, igniting the first stars, and eventually building galaxies. Only much later did dark energy begin to dominate the large-scale expansion. That timing is one of the crucial facts in this whole story. Dark energy did not have to be absent in the early universe, but it did have to be small enough for long enough that gravity could do its constructive work first. If dark energy had been too strong too early, then matter would have been pushed apart faster than it could clump together. The first galaxies would never have formed. And without galaxies, there would be no stars with heavy elements, no planets, no biological chemistry, and no observers asking why the number looks strange. This is why physicists speak of the observed dark energy density as sitting inside a narrow window. Raise it significantly, and you suppress the formation of large structures. Raise it even more, and even stars struggle to form. Raise it further still, and the universe can fail before stable atoms become common enough to matter. Push in the opposite direction, to a large negative value, and the problem changes form rather than disappearing. The cosmos then collapses too quickly under unopposed attraction, crunching before complexity has time to emerge. Life, or anything remotely like it, seems to require that dark energy be small in magnitude and astonishingly well behaved. So far, that sounds like one of those cases where observation simply tells theory what value to plug in. We measure the number, we accept it, we move on. But physics rarely lets us move on so easily. Because once quantum field theory enters the discussion, the vacuum ceases to be a passive nothingness and starts contributing energy of its own. Every field in nature carries modes of vibration, and even its lowest energy state is not as empty as common language suggests. In quantum theory, the vacuum is alive with structure. Different fields contribute to its energy, and when physicists tried to estimate how much vacuum energy should be there, the result did not come out a little too large. It came out monstrously too large. One way the source frames this is with an explicit predicted vacuum energy density of about 10 to the 45th joules per cubic meter. Another way it frames the same mismatch is as a ratio, saying that quantum expectations overshoot the observed value by somewhere between about 10 to the 56 and 10 to the 120th. The exact bookkeeping depends on how the problem is framed, but the emotional meaning is the same in both versions. Theory and observation are not separated by a factor of 2 or even a million. They are separated by an abyss so vast that it has been called the worst theoretical prediction in the history of physics. That title is not given lightly. Usually when a theory fails, it fails in a way that suggests where the repair might lie. A missing correction term, a neglected interaction, a limiting assumption that breaks under extreme conditions. Here the failure is so outrageous that it feels almost theatrical. If the quantum estimate were right in any naive sense, the universe today would not be a structured place at all. It would be an almost featureless expanse dominated by dark energy. No galaxies, no stars, no local complexity rising out of gravity. Just an expansion so overwhelming that structure never gets the opportunity to stabilize. And yet the same quantum framework responsible for this embarrassment is also one of the most successful theories ever built. That is what makes the problem intellectually sticky. Quantum physics is not a fringe idea limping along under speculative charm. It is the theory that gives us some of the most accurate predictions in science. It survives the double-slit experiment with all its weirdness. It survives tests of entanglement and Bell inequalities. It underwrites modern particle physics, chemistry, condensed matter, and the technologies of the contemporary world. We do not have the luxury of dismissing it just because one of its naive applications to cosmology goes catastrophically wrong. So the tension becomes almost unbearable. We trust the theory, we distrust the answer, and somehow both reactions seem justified. At that point, several broad possibilities open up. The first is that the different contributions to vacuum energy do not simply add in the straightforward way our roughest reasoning suggests. Perhaps there are additional contributions, perhaps from fields we have not yet discovered, that nearly cancel the huge positive terms. Perhaps the vacuum contains something like a vast hidden negative potential energy, a counterweight balancing an otherwise intolerable sum. In spirit, this is the idea the source compares to a stretched cosmic spring, something holding back the runaway value and leaving only a tiny remainder behind. That kind of cancellation is not impossible in principle, but it immediately raises a second question. Why should the cancellation be so precise? It is one thing for two large numbers to partially offset. It is another for them to offset so exquisitely that the leftover is tiny enough to permit galaxies, stars, and life. The problem does not disappear when you invoke cancellation. It merely changes shape. Instead of asking why the vacuum energy is small, you ask why the balancing act is so absurdly exact. And this is where the whole affair starts to acquire the feel of fine-tuning. Fine-tuning is one of those phrases that can be overused, but here it earns its weight. The observed value of dark energy appears not merely compatible with structure, but suspiciously compatible with structure. Small enough not to prevent atoms, stars, and galaxies from forming, large enough to dominate cosmic expansion only later, after complexity has already had time to emerge. The number looks less like a random entry and more like a value perched in a habitable slot. Of course, that by itself does not prove anything grand. Nature is allowed to produce surprising values. The universe is under no obligation to match our aesthetic expectations. But once you combine the narrow life-permitting window with the grotesque mismatch between theory and observation, the coincidence begins to feel difficult to ignore. The source puts the situation in almost personal terms. We are here because the value is low enough that matter could clump instead of being blown apart. Our atoms exist because the universe did not expand too aggressively, too early. Our existence is bound up with a numerical restraint that theory did not obviously promise. That is why Part 6 cannot stay only at the level of equations. The real shock is existential. Imagine a universe where dark energy had been somewhat larger. In that version, matter still appears, but gravity never quite gains the upper hand on the scales that matter. The first galaxies either form too late, too weakly, or not at all. Imagine it larger still, and even stellar birth becomes difficult because the clouds that should collapse into stars are instead carried apart. Larger again, and the early universe never settles into the familiar ladder of nuclei, atoms, stars and planets in the way our history did. The path to life is not just harder, it disappears. Now imagine the opposite extreme. Dark energy is large and negative. The expansion stalls early. The universe curls back inward under overwhelming attraction. There is no patient age of structure, no billions of years for stars to manufacture heavy elements, no stable middle era in which planets can cool and chemistry can wander into biology. The whole cosmic story is compressed into a violent arc too brief for complexity to take hold. Between these two failures sits our universe. And that is where the word coincidence starts to feel less like rhetoric and more like a scientific pressure point. We seem to live in a cosmos that threaded a very narrow passage between dispersal and collapse. Not zero dark energy, not arbitrarily large dark energy, not an obviously natural value from first principles. A small value, a late dominating value, a structure permitting value. Could that simply be luck? Perhaps. Physics, unlike mythology, is not allowed to reject coincidence merely because it feels aesthetically offensive. But coincidence on this scale invites explanation. The source gestures towards several possibilities. One is that some deeper mechanism, not yet known, enforces the cancellation and drives the vacuum energy down toward a tiny residual value. Another is that quantum field theory, at least in this domain, is incomplete in a way we do not yet understand. A third is that our entire reaction to the number is distorted by the fact that we are observing it from inside one universe among many possible ones. That last possibility does not yet solve the problem, but it changes its emotional shape in a crucial way. If there is only one universe, one drawer of the cosmic numbers, then the smallness of dark energy demands either a mechanism or an extraordinary stroke of luck. But if there are many universes, or many cosmic realizations with different values, then observers would naturally find themselves in the rare places where the number permits observers to exist. The coincidence would remain astonishing from the outside, but not from the inside. It would be selection, not miracle. We are not ready to go there fully yet. The multiverse and anthropic reasoning belong to the next movement of the story. But part 6 must end with that pressure building in the background. Because once the cosmological constant problem has been stated honestly, the next question arises almost by force. What kind of explanation could make such an unlikely value unsurprising? A purely dynamical mechanism might do it, if one can be found. A hidden symmetry might do it, if nature is kind enough to contain one. A deeper theory of gravity or quantum vacuum structure might do it, if our current framework is missing the right conceptual step. Or perhaps the answer lies not in changing the value inside one universe, but in changing the context in which that value is judged. Because the more one stares at this number, the more the ordinary language of chance begins to break down, and the more one is drawn toward a startling alternative. That perhaps we do not live in a universe with a bizarrely lucky cosmological constant, but in one of the very few universes where such luck was ever allowed to matter at all. That idea can sound like a cheat at first. To many people, anthropic reasoning feels less like an explanation than a refusal to explain. It can seem like a way of taking a genuine problem and dissolving it in a shrug. Of course the universe must allow observers, because otherwise we would not be here to notice it. Stated carelessly, that sounds almost circular, and in its weakest form it is. But the stronger version is more subtle, and it enters the dark energy problem for a very specific reason. It begins with Steven Weinberg, who asked whether the cosmological constant might be constrained not only by theory, but by the existence of galaxies. If dark energy can take different values in different universes or different cosmic regions, then most such regions might be sterile. Some would expand too quickly for matter to clump, others might collapse too soon. Only a narrow subset would allow gravity enough time to build stars and galaxies, and only within those rare cases would chemistry, planets, and observers ever emerge. In that setting, the value we observe would not need to be the most natural one in an absolute sense. It would only need to fall within the small band compatible with our existence. That is the heart of the anthropic turn. It does not say the universe was made for us in any theological or emotional sense. It says that any observer necessarily finds itself in a region where observation is possible. The selection effect is not the whole answer, but it changes what kind of answer is required. A value that looks staggeringly improbable in a single universe picture can begin to look almost inevitable if there are enough cosmic trials and only a tiny fraction permit complexity. To see why this matters, imagine a vast landscape of possible universes, each with a different value of dark energy. Most of them would fail silently. Some would never form galaxies. Some would form only the barest hints of structure before expansion pulled everything apart. Some would collapse before stars had time to enrich space with heavy elements. Only a small minority would allow long-lived stars, stable planetary systems, and the chemistry from which life could emerge. If observers arise only in that minority, then the mystery is no longer why the cosmological constant is small in every universe. It becomes why we expected to find ourselves anywhere else. In other words, anthropic reasoning does not predict a specially elegant universe. It predicts a biased sample. That makes it intellectually powerful and emotionally unsatisfying in exactly equal measure. Powerful because it offers a way to understand the fine-tuning without invoking miraculous coincidence or immediate design. Unsatisfying because it does not tell us why the landscape exists, how the values are distributed, or whether the multiverse behind the argument is real. It shifts the burden from one question to another. And so the anthropic move pulls us almost inevitably toward the multiverse. That word has gathered so much cultural baggage that it is easy to forget how many different ideas it now covers. The source sketches several of them, and keeping them separate matters because they do not all attempt to solve the same problem in the same way. One family of multiverse ideas separates universes by time. In such models, cosmic history does not happen once. It unfolds in repeated cycles, or eons, one following another across an almost unimaginable succession. Penrose's conformal cyclic cosmology belongs loosely in this category, though its logic is more geometric than mechanical. A big bounce cosmology can also live here, if one expanding universe follows the collapse of a prior one. In these pictures, other universes are not elsewhere in space. They are before or after us in a larger temporal sequence. Another family separates them by space. Inflationary cosmology, depending on the details, can suggest a wider reality in which our observable universe is only one patch inside a much larger inflating background. Far beyond our horizon, space may continue with regions so distant that no signal from them can ever arrive. If the physical conditions in those regions differ, whether through different vacuum states or different symmetry breakings, then each patch can act like its own universe for all practical purposes. In that case, the multiverse is not stacked in time. It is spread across unreachable distance. And then there is the quantum version, associated most famously with the many worlds interpretation. Here the branching does not happen because different cosmic bubbles inflate, or because one eon follows another. It happens because quantum outcomes that appear singular to us correspond, in the mathematics, to a continually branching wave function. Every allowed quantum history unfolds. The universe, or rather the full quantum state, does not choose one path so much as realize many. This version of the multiverse is perhaps the strangest of all, because it is tied not to cosmic geography, but to the interpretation of quantum measurement itself. Each of these ideas has a different temperament. The time-separated versions carry a kind of tragic grandeur, suggesting that endings may feed beginnings across a vast recurring structure. The spatial versions make our observable universe feel provincial, just one habitable district in a much larger and mostly inaccessible totality. The quantum versions dissolve uniqueness at an even deeper level, implying that reality continuously branches beneath the surface of what we experience as one world. Not all of them help equally with dark energy. The anthropic argument works most naturally in a multiverse, where different regions can actually realize different values of the cosmological constant or related vacuum energies. That usually points most strongly toward the spatial and vacuum landscape style of multiverse, the kind influenced by inflation and string theory. A cyclic sequence of nearly identical universes would not obviously help unless the value changes from cycle to cycle. Many worlds, depending on how one reads it, may not help either unless the branching also samples different effective constants. So the multiverse is not a single tool with one function. It is a family of frameworks, only some of which bear directly on the cosmological constant problem. This is one reason the whole discussion remains controversial. The anthropic explanation may be logically sound once a sufficiently rich multiverse is granted. But granting that multiverse is precisely where many physicists hesitate. Science, at its best, earns confidence through contact with observation. Even when theories reach beyond current experiments, they usually do so in ways that at least aim toward testable consequences. The multiverse strains that relationship. By construction, many of the regions it invokes lie beyond observational reach. Their horizons are not merely far away, they are causally inaccessible. We may infer them, we may build theories in which they arise naturally, but testing them directly is another matter. That does not automatically make them unscientific. Electrons were once unseeable too, and so were black holes in the ordinary visual sense. Science is allowed to infer hidden things from indirect consequences. The difficulty is that the multiverse, especially in its most expansive forms, can become flexible enough to explain almost anything after the fact. And when a framework explains too much too easily, the danger is that it stops risking enough to be wrong. This is why reactions to anthropic reasoning often divide along temperamental lines as much as strictly logical ones. Some physicists see it as a sober acknowledgement of observational selection, perhaps unpleasant but unavoidable. Others see it as a retreat, a sign that fundamental theory has lost the courage to demand a deeper mechanism. Both responses have some justice in them, and yet it is worth remembering why the idea became attractive in the first place. It was not invented out of laziness. It was invited by a number that seemed too small by an almost absurd margin and too perfectly placed to ignore. The anthropic explanation gains force not because it is emotionally satisfying, but because the alternative may be an even more shocking coincidence left unexplained. There is also a philosophical shift hidden inside all of this. For centuries, the great scientific instinct has been to move from local appearance toward universal law. We ask what rules hold everywhere, not just where we happen to be. The anthropic move partly reverses that instinct. It reminds us that observers are not neutral witnesses floating outside reality. We are products of a particular environment, and our observations are filtered by the conditions required for our existence. In biology, that insight feels natural. We do not expect fish to evolve in deserts. In cosmology, it feels far more destabilizing, because it suggests that some of the constants we hope to derive from pure principle may instead reflect environmental selection across a larger ensemble. That is a profound reorientation. It lowers the dignity of our cosmic address, while preserving the seriousness of our questions. Still, even if the multiverse softens the fine-tuning problem, it does not remove all mystery. Where does the larger landscape come from? Why does it have the structure it has? Why do some regions realize one vacuum state and others another? Why should inflation, if that is the mechanism, produce precisely the distribution of conditions needed for anthropic reasoning to work? And if the multiverse itself is unobservable in direct principle, how should physics decide when it has explained something and when it has only moved the question outward? These are not peripheral doubts, they are central. They are the reason the multiverse remains one of the most fascinating and divisive ideas in modern cosmology. It promises to make an outrageously lucky universe look statistically ordinary, but only by surrounding it with a reality so vast and varied that the ordinary meaning of explanation begins to wobble. So where does that leave the dark energy problem? In an honest middle ground, the anthropic and multiverse picture may help explain why we observe such a tiny value for dark energy. It may even be the least bad account currently available if no deeper symmetry or dynamical mechanism is found. But it is not a settled answer. It is an interpretive framework built at the edge of testability, and its persuasive power depends heavily on theoretical commitments that remain unfinished. That means the cosmological constant problem is still open. Dark energy has forced us toward ideas that challenge not only our picture of the universe, but our standards for what a satisfying explanation looks like. Perhaps we live in one habitable pocket among countless sterile ones. Perhaps a deeper physical principle will someday make the tiny observed value feel inevitable, without any appeal to selection. Or perhaps the answer lies somewhere stranger than either of those possibilities. And there is one more reason not to treat the multiverse as the final stop in this investigation. However vast those unseen cosmic ensembles may be, they are not the only place where dark energy may be hiding clues about its identity. Some of the most provocative hints do not come from universes beyond our reach, but from the most extreme objects within this one. Objects that may look like black holes from the outside, while concealing something much stranger within. To understand why, it helps to begin not with the exotic, but with the familiar ladder of stellar death. Our sun is massive enough to shine for billions of years, but not massive enough to end as anything especially violent. When it exhausts the nuclear fuel in its core, it will swell into a red giant, shed its outer layers, and leave behind a dense remnant called a white dwarf. A white dwarf is strange enough already. It is roughly stellar mass compressed into something closer in size to a planet, supported not by ordinary heat and pressure, but by a quantum effect known as electron degeneracy pressure. That support has limits. Add enough mass, and the electrons can no longer resist the inward pull of gravity. The remnant collapses further, protons and electrons are crushed together, and a neutron star is born. Now the support comes from neutron degeneracy pressure, and from the complicated physics of nuclear matter packed to extreme density. A neutron star is smaller still, only a few tens of kilometers across, yet can contain more mass than the Sun. Push beyond that limit as well, and the standard story reaches black holes. That progression matters, because it shows the universe already permits matter to be compressed into forms that defy everyday intuition. We are not beginning from a calm world, and then suddenly jumping into fantasy. White dwarfs and neutron stars are real reminders that gravity can force matter into regimes where the ordinary categories of solid, liquid, and gas stop being useful. So when theorists ask whether there might be something even stranger than a black hole at the end of collapse, the question is not absurd on its face. The cosmos has already earned the right to surprise us. The trouble begins when one asks how much ordinary matter can be packed into a stable object before gravity wins completely. General relativity places severe limits on how compact a conventional star can be. There is a boundary, associated with what is sometimes called Buchdahl's bound, that tells us an object made of realistic positive pressure matter cannot remain stable if it is squeezed too close to its own Schwarzschild radius, the critical size associated with a black hole of the same mass. Cross that threshold with ordinary matter, and collapse to a black hole seems unavoidable. Unless the interior is not ordinary matter at all. This is where the idea of the gravistar enters. The name is short for gravitational vacuum star, and the basic proposal is as unsettling as it is elegant. Instead of ending in a singularity hidden behind an event horizon, a collapsing object might transition into a state whose interior resembles vacuum energy, with large positive energy density and strongly negative pressure. In other words, the thing that seems to govern the expansion of the universe on the largest scales might also, under extraordinary conditions, appear inside a compact object on one of the smallest astrophysical scales. That connection is what gives the idea its peculiar charge. A gravistar is not merely another black hole alternative. It is an attempt to tie together two of the strangest features in modern physics: the fate of massive collapsed stars and the nature of dark energy. The usual image of a gravistar is simple in outline, even if the full mathematics is not. At the centre lies a region whose equation of state behaves like vacuum energy. Around it sits a thin shell of ultra-dense matter. From far away, the object can look almost indistinguishable from a black hole of the same mass, because its surface lies extremely close to where the event horizon would have been. Light bends around it in much the same way. Matter falling toward it can form similar accretion structures. The gravitational field outside is, in many models, nearly the same as that of a black hole. This is what makes gravistars scientifically interesting, rather than merely decorative. If an object can imitate a black hole closely enough, then some of the things we have identified as black holes might need more careful scrutiny, not because black holes are suddenly in danger of vanishing from physics, but because observational certainty at such extremes is hard won. We do not photograph event horizons directly in the ordinary sense. We infer compactness, gravitational influence, light bending, and accretion behavior. A very good imitation matters. The attraction of the gravastar idea runs deeper still. Black holes bring with them some of the hardest theoretical problems in physics, especially the singularity at their center and the information puzzle associated with horizons and evaporation. A gravastar, by replacing the singularity with a vacuum energy-like interior and eliminating the true event horizon, seems to promise a softer ending to collapse. No infinitely dense point, no absolute horizon beyond which information is lost forever in the most rigid sense. Instead, a new phase of matter or vacuum structure intervenes before the traditional catastrophe is complete. Whether nature actually does this is another matter entirely. The scientific community has never embraced gravastars as the default interpretation of compact objects, and with good reason. Black holes explain a tremendous amount of data very well, from the orbits of stars around the center of our galaxy, to the shadows imaged around supermassive compact objects, to the gravitational wave signals from merging black holes detected by observatories such as the Laser Interferometer Gravitational Wave Observatory. The standard black hole picture has accumulated real success. Any alternative must do more than sound intriguing. It must match that success without creating worse problems elsewhere. That is a high bar. And yet the reason gravastars refuse to disappear completely is that they remain just plausible enough to keep the door open. If their outer behaviour really can mimic black holes almost perfectly, then distinguishing them becomes a matter of subtle details. Does infalling matter emit light in exactly the same way near the surface? Do mergers ring down with gravitational wave signatures that differ slightly from true black holes? Is there any echo, any residue, any deviation in timing or spectrum that could betray the absence of a true event horizon? Those are no longer purely philosophical questions, they are observational questions, though maddeningly difficult ones. In principle, a gravastar should differ from a black hole because it has a real surface or shell, rather than a horizon beyond which classical communication ends. Matter interacting with that surface could behave differently. Gravitational waves produced during mergers might include faint after patterns or altered ring-down modes. The problem is that when an object is compressed to such extremes, those differences can become tiny. Nature is not obliged to reveal her secrets at the scale our instruments would most prefer. This brings us to one of the most provocative recent lines of speculation in the source material. Some researchers have argued that certain supermassive black holes appear to gain mass in a way that seems to track cosmic expansion itself. If taken at face value, that suggestion is extraordinary. Ordinary black holes grow by swallowing matter or merging with other compact objects. But if their interior structure were tied somehow to vacuum energy, then their growth might contain a subtle memory of the expanding universe. The source frames this as a possible clue that some black holes may in fact be gravastar-like objects, whose interiors behave more like dark energy than like classical singularities. It is a thrilling thought, because it would turn the biggest mystery of cosmology into something hiding inside galaxies, something not spread diffusely through space alone, but packed inside the very objects we thought represented gravity's final victory. Dark energy would no longer be only the agent of cosmic separation. It would become part of the story of stellar death, galactic centers, and black hole mimicry. But the criticism came quickly, and that criticism matters. Many researchers argued that the claimed growth could be explained more conventionally, or that the interpretation linking it to cosmic expansion was too aggressive. Observational uncertainties, selection effects, and astrophysical complications can easily create the appearance of a pattern before a real physical mechanism has been established. This is one of the recurring disciplines of science, and especially of cosmology. A result can be suggestive without being secure. Anomaly is not proof. Provocation is not confirmation. So where does that leave us with gravastars? In almost the same intellectual territory, dark energy itself has forced upon us. Not fantasy, not fact, but a live frontier where beautiful ideas have not yet earned the right to become accepted reality. Gravastars remain valuable because they sharpen the question. They ask whether the dark energy problem and the compact object problem might be less separate than they appear. They remind us that vacuum energy is not only a parameter in cosmological equations, but a kind of physical behaviour that, at least in theory, might emerge under extreme conditions. And they push observers to look for differences where once we may have been content with broad similarity. Even if gravastars turn out not to exist, they will have served science by making black holes answer harder questions. And that may be the real payoff of the entire journey we have taken. We began with endings: big freeze, vacuum decay, big crunch, big bounce, big rip. Each future emerged from a different assumption about what dark energy is and how it behaves. Then we stepped backward and saw how the accelerating expansion of the universe forced dark energy onto the stage in the first place. Then deeper still, into the cosmological constant problem, where the observed value looks not merely unknown, but outrageously improbable. From there the multiverse appeared, not as a casual flourish, but as one attempt to make that improbability bearable. And now, at the edge of the investigation, we find ourselves staring into black hole alternatives that hint, however speculatively, that the very thing controlling cosmic destiny may also hide in the corpses of stars. So what is the best answer we have right now? The best answer is that dark energy is real as an observed effect, but its underlying identity remains unresolved. The most conservative interpretation is still that it behaves very much like a cosmological constant, a tiny persistent energy of empty space driving the accelerated expansion of the universe. If that interpretation holds, then the most likely long-term future remains a form of heat death, a great thinning into darkness, remnant matter, evaporating black holes, and eventual thermal stillness. At the same time, that answer is not complete. We do not know why the vacuum energy is so small. We do not know whether it is truly constant forever, or only appears so on the timescales we can observe. We do not know whether the right explanation is a deeper field, a hidden symmetry, a multiverse selection effect, a revised theory of gravity, or some connection not yet fully imagined between the large-scale expansion of space and the most extreme compact objects within it. And perhaps that is the most fascinating part of all. Dark energy does not simply threaten the universe with an ending. It exposes how incomplete our understanding of the universe still is at the deepest level. It touches the future of all structure, the origin of cosmic habitability, the credibility of our best theories, and the possibility that empty space is not passive emptiness at all, but one of nature's most active and least understood ingredients. We may already know what dark energy does, but we still do not know what it is. And until we do, the universe will keep its final secret partly hidden, not because it refuses to speak, but because it is speaking in a language we have only just begun to hear. If this left you with your own view of which possibility feels most convincing, I'd love to hear it. And if you enjoy this kind of quiet cosmic mystery, staying with the channel is a gentle way to keep exploring it with me.